Welcome back. Next part 3.4 of current electricity, Ohm's law. A basic law regarding flow of currents was discovered by J.S. Ohm in 1828, long before the physical mechanism responsible for flow of currents was discovered. Imagine a conductor through which a current I is flowing, and let V be the potential difference between the ends of the conductor. Then Ohm's law states that V is directly proportional to I. V is equals to Ri. R is constant to remove the proportionality sign, where the constant of proportionality R is called the resistance of the conductor. The SI units of resistance is Ohm and is denoted by the symbol, this one, Ohm. The resistance R not only depends on the material of the conductor but also on the dimensions of the conductor. The dependence of R on the dimensions of the conductor can easily be determined as follows. Consider a conductor satisfying equation 3.3 V is equals to Ri to be in the form of a slab of length L and cross-sectional area. Figure 3.2a. This one. Imagine placing two such identical slabs side by side. Figure 3.2b, this one, so that the length of the combination is 2L. The current flowing through the combination is the same as that flowing through either of the slabs. If V is the potential difference across the ends of the first slab, then V is also the potential difference across the ends of the second slab, since the second slab is identical to the first and the same current I flows through both. The potential difference across the ends of the combination is clearly sum of the potential difference across the two individual slabs and hence equals to V. The current through the combination is I and the resistance of the combination RC is RC equals to 2V by I gives to R. Since V by I is equals to R, V by I is here represented as R, so that is become 2R. The resistance of either of the slabs, thus doubling the length of a conductor doubles the resistance. In general, then resistance is proportional to length. R is directly proportional to length. Next, imagine dividing the slab into two by cutting it lengthwise so that the slab can be considered as a combination of two identical slabs of length L, but each having a cross-sectional area A by 2. For a given voltage V across the slab, if I is the current through the entire slab, then clearly the current flowing through each of the two half slabs is I by 2. Since the potential difference across the ends of the half slabs is V, that is the same as across the full slab, the resistance of each of the half slabs R1 is R1 equals to V by I by 2 gives to V by I. I told you V by I is represented as R, it is 2R. Thus, having the area of the cross section of a conductor doubles the resistance. In general, then the resistance R is inversely proportional to the cross sectional area. R is inversely proportional to area, that is 1 by A. Combining equations, R is directly proportional to, inversely proportional to, actually the equation is L by A. Directly and inversely proportional to length and area respectively. And hence for a given conductor, R is equals to rho L by A, where the constant of proportionality rho depends on the material of the conductor but not on its dimensions. Rho is called resistivity. Using the last equation, Ohm's law reads V is equals to I into R equals I rho L by A. Current per unit area taken normal to the current I by A is called current density and is denoted by J. The SI units of the current density are area per meter square. Further, if E is the magnitude of the uniform electric field in the conductor whose length is L, then the potential difference V across its ends is EL. Using this, the last equation reads E is equals to L equals to JPL, or E is equals to J rho. Actually this is also rho, by mistake I have said P. The above relation for magnitudes E and J can indeed be cast in a vector form. The current density, which we have defined as the current through unit area normal to the current, is also directed along E and is also vector J E by E. Thus the last equation can be written as E is equals to rho J. J is equals to sigma E, where sigma equals to 1 by rho is called the conductivity. Ohm's law is often stated in an equivalent form. Equation 3.13, this one, in addition to the equation previous one. In the next section, we will try to understand the origin of the Ohm's law as arising from the characteristics of the drift of electrons.